All right, so rules of exponents. What we're basically going to do is explain how we can use powers to keep track of common factors in certain situations. So we've done this before. The first example we have, we notice that it's one term, and the parentheses are just monomials, or a single term each. So in terms of composition, when we have a single term times a single term, we can just look at the individual factors in any order. So when we do this, we can take the constant factors, -2 and 5, multiply those together. We would get a -10 factor. And then our variable factors, x squared times x to the fourth, this is where we use our powers to basically count up all the factors. So x squared is 2 factors of x, x to the fourth is 4 factors. We're going to combine those together, and that would have a total of 6 factors of x. So we just add those exponents. So basically, when we're multiplying these repeated or common factors, we're just using the exponents to count common factors, basically, or to count up common factors. So you might see this written in algebra, in an algebra book like this. So you got x, a factor of x times a factor of x, and say the first factor is raised to the mth power and the second to the nth, and I'm multiplying these factors together. So what this is equal to is the same factor x raised to the m plus n power. Just add the exponent. All right, so what's important when we're multiplying monomials, or we have a single term, then we basically use the factors to count up the common factors and write the factor for that sum. So the next property we use with quotients, we use with factors, and the idea was that we cancel fractional factors of 1, and basically that's like x over x, that equals 1. So but the main idea is to keep track of factors that are left. So if we notice the composition here, this is a one fraction. The numerator is just one term, and the denominator is just one term. So everything in this expression, everything in this term is a factor. So in terms of composition, what we're looking for is a fraction where the top is one term and the bottom is one term. So this would be a term over a term. So what we're going to do is take each factor and work with them individually. So in the numerator, we see maybe like 15. We could split up into a factor of -3 and 5. X to the fourth, that's like 4 x's, right? So x times x times x times x, and then times y, the last factor. On the denominator, we have a factor of 5, 2 x's, and a y. So when we cancel fractional factors of 1, we're basically just multiplying those factors that give us 1. So 5 over 5 is 1. Well, that's not going to contribute to our answer, so we can just cancel. X over x, those are both 1s, and then y over y. So now we just need to keep track of factors that are left. So it looks like there's a factor of -3 in the numerator left, and two factors of x left, so that'd be x squared. So the properties of exponents, if we go back, we can use the exponents in our canceling to keep track of factors. So again, we could use the canceling idea with our factors. We can go back up here and just work with the expression as we see it. And the 5 can cancel with the 15, leaving, and this would be the -3. So what we can do here, since we don't have a lot of room, we can just start constructing our answer. So we have a factor of -3 left. Now, if we look at the x's, we can use the exponents. So there's two factors of x in the denominator and 4 in the numerator. So all two of these factors will cancel, leaving two factors in the numerator. So this x squared that's left, we'll just write that in the numerator. And then the y's, we notice those just cancel, leaving a factor of 1, and we don't need to write that. So again, we'll practice this, but it's something hopefully that we're using. We're using the exponents as we cancel, and then we keep track of factors that are left. Again, the composition, we want to make sure that we're looking for is a term over a term. Then every factor in the expression can be considered individual. All right, now to some exponent rules we haven't seen. So here's a situation where we have a set of parentheses, and in that parenthesis is a factor raised to a power. So we have an outside power. This 3, I like to call outside power. If we apply that power, then it's basically saying we need 3 copies of the factor that's inside. So this would be like writing 3 factors multiplied together of x squared. That's what powers represent, repeated factors. So when I have repeated factors, I'm just adding up exponents. So this is 2 plus 2 plus 2, or it'd be the same as x to the 6th power. So what I want to try and do is figure out how can I use the exponents in the original problem to come up with our answer. So let's try another one. Again, we see the same situation. We have inside parentheses, and we have this outside power. So if we apply the outside power, that would give us 4 copies of y to the 7th. So we'd have 4 factors, 4 repeated multiplications of y to the 7th. So that's 4 repeated additions, right, of 7. So when I have this, I can just use the powers to add up how many factors of y I have. 7 plus 7 plus 7 plus 7 is the same as 4 times 7. So this would be y to the 28th power. All right, so in terms of composition, we have a set of parentheses and an outside power. Inside the parentheses, we just have a factor. So if I'm raising a factor, and this factor could be raised to a power, but if I'm taking a factor to a power, then all I need to do is multiply exponents. So that's the rule. Just multiply exponents. So in an algebra book, you might see it written like this. You might see in parentheses x to the mth, and then all that's raised to the nth power. And what they're saying is then you could rewrite this as x to the m times n. So the composition is just that factor in parentheses to a power. And then we just multiply exponents. All right, so again, we'll practice with this, but I want to go through the last one, really the one that kind of puts these together. What happens if you have a situation like this? It's very similar to the one we just did. You notice we still have parentheses, and we have this outside power. So again, we'll go through this. If we apply the outside power, this is a power of 3, so I want 3 copies of negative 2xy squared. And now we're just multiplying terms. This is just one term. We're multiplying individual monomials. So what we can do is group all the factors that are alike together, and we'll end up with 3 factors of negative 2. Whoops, I'll just do that. 3 factors of negative 2. We'll end up with 3 factors of x. So all the x's will end up with 3 individual factors of x. And you notice we also have 3 individual factors of y squared. So we have y squared. Sorry. Anyway, y squared, and y squared. So we could rewrite these. So you notice we could say this is the same as negative 2 to the third power. So this factor raised to the third power. We also have an x, a factor of x, and that's raised to the third power. And then we have this factor of y squared, and that's raised to the third power. So we could finish this problem with properties we already know. Negative 2 cubed is a negative 8. So that would give us a factor of negative 8. Negative 2 times negative 2 times negative 2. Well, x to the third power is just x cubed. And then y squared to the third power, we multiply exponents, would be y to the sixth. So what's happening is that now I have a full term inside. So in terms of composition, I have a term to a power. So it'll look like this. I got my parentheses. Inside I have a term, and this term could consist of a whole bunch of factors. We have a term to a power. So what do? It looks like from this part, it looks like we can apply the power, we can apply the power to every factor in the term. Now I'm going to add to this a little bit, but that's in a nutshell what we have. If we have a term to a power, that outside power gets applied. We're going to apply the power to every factor in the term. So let's try that with this one. The next problem, or the next example, and I'm just going to scroll down a little bit. Again, we notice the parentheses and this outside power of 2. So we're going to take every factor in the term. So we have a factor of 5. And we're going to apply the power of 2. We have a factor of a cubed. And we're going to apply the factor of 2 to that. And then we have a factor of b to the fourth. And we're going to apply the factor of 2 to that. You notice every time we do this, we're always ending up with a factor to a power. So if we get our answer, 5 squared is 25. And then we're multiplying exponents every time we have a variable factor to an exponent. So this would be a to the sixth. and b to the 8th. So we can combine this. We can apply, I'm just going back up here. We can apply the power to every factor in the term, and we can also do this. We'll multiply exponents, or multiplying exponents. So this is actually one of the most important properties of exponents that we have, is when we have a term to a power. So this is a big one. We have a term to a power. We're going to apply the power to every factor in the term, multiplying exponents.